Okay, I've got a set of different size squares here. Well, what I'm going to do is to try putting some squares together like this to make a triangle shape on the inside between them. Okay, so there's one triangle we can make. Of course, some combinations of squares just won't make a triangle at all because the sides are too short. So this won't work, this won't work, and it depends what squares we've got, what sort of triangle we get, if we get one at all. But here's one particularly interesting triangle. You can see what's special about it. It appears that this here, this angle here between these two smaller squares is a right angle. And that's what this video or series of videos is about. It's about the relationship in a right angle triangle, the relationship, the areas of these two squares and the area of this larger square. So if I turn these squares over, you'll see they're marked. This one is marked as a 3 by 3, this one a 4 by 4, and this one a 5 by 5. The other squares are marked as well. But we've done that so we can look at the areas of these 3 squares that go to make up a right angle triangle in between. Let me just rearrange them a little bit. Here we are. There's our right angle again. And we have what's called a 3, 4, 5 triangle. 3 units here, 4 units here, and 5 units here. I've said before, it's to do with the areas of these squares. What's the area of this? Well, it's 3 by 3, which is 9. This one, yeah, 16. That's 4 by 4. And this one, 5 by 5, is 25. Now if we look at the areas of these squares, how they relate one to another, I think we can see, you can pause the video to count if you want to, we can see that the area of this square is equal to the 2 areas here added together. And that's basically all there is to this famous theorem of Pythagoras, named after Pythagoras, Pythagoras' theorem. That's all it is. If you've got a right angle triangle, these 2 smaller squares, their area adds up to the area of this square. Okay, now I've got a triangle prepared that just fits inside, so you can actually see the triangle we're talking about, the 3, 4, 5 triangle. And I've got some copies of it because I'll show you something interesting. If we take this triangle and take copies of it like this, putting them round the largest square, we produce another square. Again, the numbers involved are 3, 4, 5. Here's a 3 and a 4, making 7. 3 and a 4, 7. 4 and a 3, 7. 4 and 3, 7. This is a 7 by 7 square. We can also take copies, more copies of this triangle, and we can fit them down here like this. And I think you might be able to see the start of another large square here. This one was 3 and 4 on the side. Here we've got a 4 and a 3, 4 and a 3, 3 and a... I've got one here, which hopefully will make things clear, because what we're doing here is making 2 of the large 7 by 7 squares, but they're overlapping. Look at this one first, the one we just made. It's 7 by 7. Now look at this one. it's 7 by 7. Now the interesting thing about these two separate squares are they are made up with 4 triangles and other bits. Here we've got 4 triangles and, make it clearer, 4 triangles and our original large square. If we look at this square now, it's 1, 2, 3, 4 identical triangles and these 2 squares. So if these 2 squares, large ones, they've got the same area, they've got to. If each of those is made up of 4 triangles and other bits, then those other bits must be equal in area. In other words, this area must be equal to this area. And again, that's all Pythagoras' theorem says. Okay, what I've done here is to separate the figures out just to make this business of the 2 large squares a bit clearer. If I take yet another green triangle, clear this away, last green triangle, we can now see perhaps more clearly our 2 7 by 7 squares. Each one has 4 green triangles inside and the rest is made up with squares. So the large square is made up with these 2 in this case and with this one in this case. So clearly the area of this square is the same as the area of these 2 squares.